Let's talk about what makes incompressible substances special, and particularly how you can use the specific heat definitions to do interesting things with incompressible substances if you know they're incompressible. So what does it even mean to be incompressible? Well, the simplest definition that's appropriate for us is that you have constant specific volume. What you can imagine is that you have some stuff in a piston, and you try pushing on it or pulling on it, and it just doesn't change volume very easily because either it's a solid, or if you think about it, even a liquid. If you try pushing or pulling on water, it's really tough to change the density of water. It's approximately the same across a broad range of temperatures and pressures. Water is approximately incompressible under most circumstances. We'll also be using the two specific heat definitions, so from your lecture notes, the specific heat at constant volume, CV, is given by this expression, and the specific heat at constant pressure is given by this expression. Note that those are partial derivatives, and the subscript outside the derivative is telling you what is being held constant. Okay, so how are incompressible substances special? Well, let's start with the definition of CV, which I repeat over to the right. For a specific volume that's approximately constant, which remember is what it means to be incompressible, then we can actually change this to a full derivative of U with respect to temperature. Okay, already alarm bells should be going off. How can I go from that top line to the third line there, turn a partial derivative into a full derivative, just by knowing that V is constant? The answer has to do with a small detail in one of your earlier lecture notes that you may have missed. So in Lecture 7, I actually go through the state principle for simple systems, and it's also discussed extensively in your book. What that means is that for a simple system, more fully explained again in lecture notes or the book, there are actually only two independent physical properties that you can measure. So what we've done here is we've said that we're holding one of them constant, so we're holding V constant. Well, if that's true, then actually the only other variable that we would need to consider for the internal energy could be temperature. Therefore, du dt is a full derivative with respect to temperature. There are no other variables that we need to consider as long as we've held V constant. Okay, so what about the specific heat at constant pressure? Well, that is normally written partial h, partial t with fixed p. We can write out the full expression for the specific enthalpy. So little h is little u plus p little v. Well, in that case, if we're holding V and P constant, wait a second, where do I get that? Well, we already said that we're considering an incompressible substance, so little v has to be constant. P has to be held constant in the specific heat for constant pressure. It's even in the name, right? That little subscript P tells us we're holding P constant. So we can write Cp alternately as being the partial derivative with respect to temperature of the quantity U plus PV. And remember, we're holding both P and V constant. We move this up a little bit. That becomes a much simpler derivative. If P and V are constant, that second term just goes away, right? Its derivative with respect to anything, including temperature, must be zero. So now Cp just becomes the partial of the internal energy with respect to temperature, holding P constant. Now we're going to use exactly the same trick that we just used for Cv. Partial U, partial T with P constant. Well, let's pick our two variables to fully specify this system as pressure and temperature. In that case, we're holding P constant. We can rewrite this as the full derivative of U with respect to temperature. You may notice something. Cv up here is equal to du dt, full derivative. Cp down here is equal to du dt, full derivative. That means that Cv must equal Cp. So that's true only for an incompressible substance. Obviously, if it were true all the time, we wouldn't have defined the two different specific heats. But in this case, for an incompressible substance, Cp and Cv are one and the same. They have the same value. So let's go ahead and just write that, Cp equals Cv, and I'm going to define just another specific heat I call C. The subscript doesn't matter anymore, so we can just refer to all specific heats as C. It's not the speed of light, of course. We can also define the ratio of Cp to Cv. Well, in this case, that's 1, right? The ratio of a number to itself is 1. And because we know that Cv equals du dt is constant, and because the derivative is constant, we can rewrite du dt as the ratio of differences delta U over delta T. So that still has to equal C, our generic specific heat. Okay, let's expand out those two deltas. Well, it becomes U2 minus U1 equals C, T2 minus T1. That's a very useful shortcut that we can use. So if we know that we have an incompressible substance, and we want to figure out the difference in internal energies as a result of some heating process, presumably, then if we know the temperature difference and we know the specific heat, you can figure out the change in internal energies automatically. That's way easier than having to look it up in a table. Okay, so let's move that up. That's our first interesting and useful result. We'll save that for later. What else can we do? Well, we can immediately say that delta H, the change in specific enthalpy for an incompressible substance, well, given that the specific enthalpy is U plus PV, delta H must be delta that whole thing. So we can expand out the delta. Delta H equals delta little u plus V delta P. Remember, we assumed it's incompressible, so little v has to be constant, right? Alright, so in that case, we can substitute in an expression for delta u. We have one up there in the box. It's that delta u equals c delta t. So that means, lower down, delta h must be c delta t plus v delta p. Let's expand out the deltas, and that gives us our second useful shortcut. H2 minus H1 equals c, the specific heat, times the temperature difference, plus little v times the pressure difference. So once again, if you need to know the specific enthalpy difference, all you need to measure are the pressure difference and the temperature difference, know the specific volume, which is constant, and know the specific heat. Generally speaking, things like pressure, temperature, specific volume are direct measurables. They're pretty easy to get at. Things like internal energy and specific enthalpy, those are tough to directly measure, but you can infer them immediately from knowing these other things in an incompressible substance. That's pretty nice.